In this study, we examine a class of rearrangement problems where items to be sorted are stored in a lattice-like storage. The setting frequently appears in our daily lives. For example, arranging shoe displays at stores, the seasonal adjustment of a shoe collection, organizing a wine cellar, or alphabetizing books on bookshelves. In rearranging the items, we assume a pick and swap model, where the robot may pick up or drop off items, move around, and make item swaps. For such a problem, a plan P may be fully specified as a sequence of n-effector locations P0 through Pn plus 1, where P0 and Pn plus 1 correspond to the n-effector rest position, usually at the top left of a lattice. We would like to seek a plan that minimizes the time it takes to solve a rearrangement problem where each pick and swap has a cost Cp and n-effector travel has a unit distance cost of Ct. The optimization is performed sequentially, first minimizing the number of pick and swaps and then the n-effector travel time. Under the setup, we examine 4 settings in detail, labeled one-dimensional problem, or LOR, partially labeled one-dimensional problem, or POR. In a POR problem, items are sorted into different types, where items within the same type are interchangeable. Labeled two-dimensional problem, or LTR, and finally, partially labeled two-dimensional problem, PTR. We highlight our algorithmic results with provable guarantees. For LOR, we may minimize the number of pick and swaps using a cycle following procedure. For this example, we may first follow the cycle 3-4-1, which uses 3 plus 1 equals 4 pick and swaps. This solves the problem for items 1, 3, and 4. For the 2 cycles of this problem, 3-4-1 and 9-8-5-7-2, a total of 10 pick and swaps is needed. We then further minimize the n-effector travel. We observe that following cycles 1 by 1 may incur additional n-effector travel. In this example, following the cycle 4-1 and then 5-3 incurs a total distance cost of 14 units. If we switch in the middle, that is, we start cycle 5-3 before finishing 4-1 and then continues with 4-1, we can actually save 4 units of distance traveled without adding more pick and swaps. Together, cycle following and cycle switching yields an optimal algorithm for LOR. For the partially labeled setting, POR will again solve it by cycle following. However, because an item does not have a unique destination now, the cycles are not unique. Here, we need to first perform a matching, which induces a set of cycles, in this case, these 3. These cycles can be merged to reduce the number of pick and swaps. The first type of merging does not add more distance cost. We can perform it like this. The second type of merging, performed like this, adds additional distance cost. We can minimize the additional distance incurred in this manner by computing a minimum spanning tree over all affected cycles. Combining cycle following, cycle switching, and cycle merging yields an optimal algorithm for POR. Moving to the 2D settings, we can show that minimizing the end effector travel is NP-hard for both LTR and PTR. Nevertheless, a greedy cycle following procedure can still do quite well because the number of cycles in a random permutation is quite small. This fact is exploited elsewhere, for example, in Trelevan's work on pick-append delivery problems, and was perhaps first publicized in the 100 prisoners problem. Because travel within a cycle has fixed cost, and travel between cycles can be ignored, a cycle following algorithm is actually asymptotically optimal for solving LTR problems. We can further improve the algorithm for LTR by adding cycle switching. For example, we can use cycle switching to shortcut this cycle following solution to reduce the end effector travel. This leads to improved optimality when the number of items is small. Similar computational results hold for the partial label setting, which we do not elaborate here. Simulation results further confirm the efficiency of our algorithmic solutions. In general, we observe that our optimal or optimized solutions provide a sizable improvement in terms of optimality. To conclude, in this study, we proposed the lattice rearrangement problem and the novel pick and swap model, studied the structural properties of many variations, and developed high-performance algorithms for all. Our results generalize to higher dimensions.